Let's do a video on a Bode plot of a high-pass filter, which is a special case um, because when the root is at 0, right, and in this case we have 3 roots at 0, you don't really have a starting value, right, because 20 log of 0 is undefined, and you can't plot 0 on a log scale. So there's no flat point at a low frequency that you can take a baseline and then start plotting from there. All right. So that is kind of a special case. All right. So let's just go through it. This assumes that you are somewhat familiar with Bode plots and why we do what we do. Okay. So again, this root at omega equals 0, it's always active. So it's omega isn't going to be less than 0. So we have our cases of these 3 frequencies, these 3 break frequencies, because they're all real. It's easy to do, of 440 kiloradians per second. So when omega is a lot less than 4, right, this term, the S term, drops out. You're left with 4. This S term drops out. You're left with 400. And this S term drops out. You're left with 40K. So you multiply everything together, but you can turn that into 60 log of S divided by 100 by taking the cube root of the denominator and the numerator and then multiplying the log by 3. So that's where we get our 60 dB per decade from. All right? And this would just be a line, right? And at 0 dB, you would be at 400 radians per second. Okay? Then the next is when we're greater than 4 but less than 400. So now omega is greater than 4, much, much greater. The 4 drops out. But in this case, the S term and the S term still drop out, and you're left with S squared divided by S, 400 times 40K, which is S squared divided by 16 meg, which you can turn into a 40 dB per decade line by taking the square root of the numerator and the denominator. So basically, now we have another slope, not as sharp as the other one, and the 0 dB point is at 4K. Now, what about when we are less than between 400 and 40K, right? The 4 drops out, the 400 drops out, so we get S cubed divided by S squared, 40K, right? Which now, that's just a 20 dB per decade line, and the 0 dB point is at 40 kiloradians per second. And then we take our final frequency range of omega much, much greater than 40K, right? And all the breakpoint frequencies now drop out. We have S cubed divided by S cubed equals 1, which is 0 dB, or no slope. Now, the thing is you could, at this point, use that as your starting point and draw backwards, okay? Which is probably the easiest thing, and that's what I showed in class the other day. All right, but I know a lot of people like to see an algorithm. So here, I've summarized it. We've got 4 asymptotes: the 60 dB per decade line, the 40 dB per decade line, and the 20 dB per decade line. And they all cross 0 dB at various spots. Right, and then we have this flat region. And what my little note is trying to say, if I can get at it, is that this can be hard to get the y-axis right, or done correctly. Now, yeah, I was able to kind of do it in the first shot, but that's kind of with a lot of experience. So I just knew that I needed 0 dB because I have all these intercepts at 0 dB, right? And then if the slope is positive and you're reaching 0 dB, well, I'm going to need a lot of negative, right? And if 0 dB is the highest gain, I know that most of the y-axis is going to be negative. So I just start stepping it out of, trying to draw it decently, minus 20, minus 40, 60, 80, 100, minus 20. and then just trying to draw this plot. So the 60 dB at 400, I just take that point, I go over a decade, and I go down approximately 60 dB, and then I just, extend the line. The next asymptote is 0 dB at 4K, and now I only go down 40 dB per decade, and then I draw this line. And this is where it gets a little bit difficult, because this is a hand plot, right? Is that this intersection, right, needs to happen near 4, okay? And even still, I'm not exactly right. I needed to actually extend this line even more. Here, I'll try to do it right now. Oops. Is I'll start here. Okay. The 4 is that break point. Okay. So I have to kind of and the point of this is really hard to get right. So even here I might have not scaled it properly. So let me try to extend this 60 dB per decade line even more. Now let me come back here. I have to intersect at that 4. Right now that one's a little bit better, okay? But see how I had to really play around with it, okay? Now I would have accepted that on an exam because it's pretty close and it's a hand plot. But you want to make sure that these breakpoints are labeled like, 4, right? That's happening at 4 radians per second. This breakpoint is happening at where's it happening? $400. Okay, right? Because it was 440K. So this starts here, but this line, yeah, even I gotta tell you, I have the breakpoints, they're off. This one is even off more, and actually, I will have to redraw it to get it right. Okay, so the problem is I've kind of got this y-axis, but I didn't really know how far to extend it, right? So again, if I saw, here's the thing, what do I really need to see, right? Well, there's a place where I've got 60, then 40, then 20, and then flat. This happens at 40K. That was, I believe, 400, and this one was 4. Now, yeah, the distances along the x-axis aren't quite right, but by entering in the slopes, 60 per decade, 40, 20 per decade, and then just flat 0 dB, I get the idea of what's going on, and you would too. All right. So you can spend a lot of time trying to make this plot correct, following that particular algorithm, but again, even I'm struggling to do that. Okay. Where what I can do is leave the y-axis kind of arbitrary, right? So I know that, let's try red. So the first line, right, it's 60 dB per decade. So there's 1 decade, and I'm just calling these out 20. So 20, 40, 60, okay? So this is a little bit better, I think. All right, and I'm just going to draw that asymptote. Like that. And that's the 60 dB line. The next line would be 40, right? And it changes, right, from 60 to 40 at 4 because that's the break frequency, right? So right here, now I just need to go over a decade, right, and down 40, which is about here, right? Oops. And that's the 40 dB per decade. But you can see that that point at 4 is clearly it's breaking there, right? And of course the lines have to intersect, right? So then the next breakpoint is 400. Now I don't have to figure out where it's going to be because I can fill that in later. I just know at 400, when I go over a decade, right, I only go down 20. All right. And then here at 40K, right, I know that it'll go flat, okay, at 0 dB. So the thing is now I've got my curve laid out, right? I can now kind of highlight it to say that's my 60, and you should label 60, 40 dB per decade, 20 dB per decade, and then just 0 dB. And really, that's kind of all you need to know, because if I start off at, actually, so now I know where 0 dB is, okay? This is now 0 dB minus 20, 40s, and now I know how to plot it out properly, right? So, and that's kind of a special case for the high pass because it's got a constant gain at high frequency. The low pass, if this were reversed, right, I could do something like this, right? And let's say, totally different example. This was 20 dB, right? Oh, well then I would just put 20 dB per here and then scale it down from there and making sure that, okay, this is at 4K and this one is somewhere between 400K and 4 meg, right? And I would just label these plots as like minus 20 dB per decade. I'm leaving off the complete slope because I'm trying to, okay, which is much faster. Now in the previous video, the shape did something like this. It went here, sharp, and like this. There was no starting point, okay? So yeah, you had to do it this way, but so that makes it, at which you could make a mistake, which I did. And doing that video took me all day. I had made so many mistakes. All right. And so that's why this kind of shape, and again, this is magnitude, right? And it looks kind of like a bandpass. I wouldn't ask you to do. All right. And then just to finish it off, right, I just found that doing the phase by table is pretty much the best way. And then what's the starting point? Well, S cubed is J omega cubed, but rather than, it's better to put it into polar, omega with phase of 90, omega phase 90, omega phase 90, then you get 270 and omega cubed. Put it that way, you should get the right answer. And then that, yeah, this pole at 4 gives us minus 45 at omega naught, or at 4, 0 at a tenth and below, and minus 90 degrees phase at 10 times 4 and above. And so I just sum across these columns, right? And I get this shape because basically I was trying to make it so it all worked out evenly. Like, so I have 4, which is the square root. You can make the square root of 4, square root of 400, an integer. Square root of 40K is an integer. So they're all kind of close. And that's why the phase is this kind of straight line. But you have to understand, there's even with just two real poles, there's many kinds of questions that one could ask in relation to poles. All right, so you probably could try. I would try to evaluate which method to go for first. But on an exam, really, it'll either be a constant frequency at low frequencies, or a constant gain at low frequencies, or a constant gain at high frequencies for this exam, right? But in life, you could see many kinds of Bode plots, like band or things like that. So I hope that helps.